Hi students, this is Mr. Yao. Today we're going to talk about 10.5 and 6, where we will learn more about conditional probability and explore a bit more about independent and dependent events. First, let's do a quick review about two-way frequency table. For this table, out of all of the boys, what is the percent of those who do not attend football games? So boys first, out of all the boys are right here, that's 87. And out of these 87, we're trying to look for how many do not attend the game. So it's 42 out of 87. And of course, we change that into a percent. So 42 divided by 87, that is 0.48275, which change into percent, 48.28%. And that is a conditional probability because we have a condition first. We're going to look for all the boys first, and then within all the boys, we're going to look for who do not attend football games. So let's have a look at the definition again. We just computed the P not attending football game given boy. This is the conditional probability of someone not attending the football game given that they're boys. Here's the formula for computing the conditional probability of event A given event B. The formula is as follows. P, the probability of event A given event B, equals to the probability of A and B over the probability of B. So like making sure both of them are happening compared to just the condition event happening. If we multiply both sides by this probability of B, we can get rid of it from the right side, which just leaves the probability of A and B. And then the other side is going to have probability of A given event B times the probability of B. Of course, A and B can switch back and forth, but that's the basic idea. And now, how can we actually use that formula on this question? Just to be clear, this question is basically now becoming probability of not attending given boys. So that's basically our event A, and that's our event B. So A given B. It's the same as the probability of not attending and boys. Over the probability of just boys. Okay, because that's our B. And the probability of not attending and boys is right here. 42 out of 140. On the bottom, the probability of just boys, that is going to be the 87 out of 140. Now we have learned before, if you have a fraction on the top and the bottom that share the same denominator, we're just going to multiply to get rid of it. So the 140 is gone. We're just left with 42 over 87, which is actually the same as the previous one. But just now, we're using the conditional formula to calculate that. Next, let's use that in an example. What is the probability a randomly selected person is male given that they own a pet? Given that they own a pet. So that's our condition. We can write it as probability of male given the condition, which is have pets. Right, so we can actually write it as male, that is boys, so 98 out of 200, and compared to have pets. Oh, sorry, the first one is actually male and have pets. Male and have pets, that's 82 out of 200. And the bottom is just have pets, which is 172 out of 200. The top and the bottom both have the 200, so they're gone. We're left with 82 over 172, which can be simplified to be 41 over 86. That's example 1. Next, 70% of your friends like chocolate and 35% like chocolate and like strawberry. What percent of those who like chocolate? Those who like chocolate. So that's our given event. The probability of strawberry given chocolate. Use the strawberry and chocolate, which is 35%, divided by just the chocolate, which is 70%. So that is going to be 1 over 2. That's example 2. Next, we have a bit more definition about independent and dependent events, which we can also refer to it as with replacement or without replacement. So now let's have a look. Events are independent if each event is not affected by any other events. Independent, we have learned this already. The probability of A and B together, if they're independent, is the same as probability A times the probability of B. They're dependent if they actually affect each other or affected by the previous events. And that is, for example, taking marbles out of the bag without putting them back, which changes the next pick. So in that case, we're basically saying we have an event B happening given event A happened first. So the probability of A and B is the same as the probability of A times the probability of B given A already happened. So that is dependent. And now with replacement, because when you put it back, when you actually replace it, that means you put it back. The next pick, you still have the same kind of probability that works the same way, which means they are independent events if we have with replacement. Then on the contrary, without replacement, that means the events are dependent. Now let's have a look and do some practice. Example 3. Given a bag with 6 red marbles, 8 blue marbles, 4 yellow marbles, 7 purple marbles, and 9 green marbles, one student chooses a marble and put it back. Put it back. With replacement, that means it's going to be independent. Now, what is the probability that the first student chooses a yellow marble and the second student also chooses a yellow marble? We're not going to write the whole thing in the probability, like student A chooses yellow marble, student B. No. I'm just going to simplify it a little bit. So I'm going to write yellow, 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 comma, and another yellow. So this represents the event, the first event. This represents the second event. If we have more, we're just going to use comma to keep separating them and keep writing inside the same parentheses. So let's see, how many yellow marbles do we have? We have 4 yellow marbles out of, in total, 6 plus 8 plus 4 plus 7 plus 9. And that is going to be 34. Got them? So 34. Then since we're putting it back, it doesn't affect at all, so that probability is still going to be 4 out of 34. And after you multiply the fractions and simplify them, it's going to be 1 out of 289. That's part B. Part C, what is the probability that the first student chooses a red marble? The first student chooses red, and the second student chooses a purple marble. Let's have a look. Red marble, we have 6 of them. And then out of 34, that's the total since we're putting it back. So the next round that you pick is still out of 34. And we have 7 marbles. So in that case, that's going to be, the second one is actually 7 purple marbles. So now we can calculate it. The top is going to be 21. And the bottom is going to be 578. That's part C of example 3. Next, number 4. You have a deck of cards to play a game. Your friend chooses a card and keeps it. This time, keeps it. That means they're not putting it back, so you have one less card to choose from. In that case, the events are being affected, so it's dependent. What is the probability that your friend chooses a red card and you choose a black card? So choose a red card, red, and the next one is black. And you can also be more precise and write it as black after red, which also means they're being affected. So first red cards, we have 26 red cards out of 52. And then, since no one actually put it back, the friend didn't put it back, now we have one less card, so it's going to be out of 51. But there's no black cards being changed, so it's still going to be 26 out of 51. And start simplifying things. That's a 1, that's a 2, that's a 13. Actually, they can't be simplified. So it's just going to be 26 out of, actually not 26, 13 out of 51. Part C. What is the probability that your friend chooses a diamond? So probability of diamond. And you also chooses a diamond. So diamond, diamond. We have 13 diamond cards, 13 out of 52. After picking out 1, though, we have 12 left. So the first one, that's 1 and 4, and this is 3. So it's going to be 3 out of 52. Part D. What is the probability that your friend draws a king first? Probability of king first, then you also draw a king. 52 cards in the deck, but there are only 4 of them being king. And since somebody drew it and didn't kept it, so now it's going to be out of 51 because there's 1 card less. Since the king is already picked out, you actually have 3 kings left. So that becomes a 1, 13, that's 17. So the final probability is going to be 1 out of 221. That is example 4. Now more practice. 7 dimes and 9 pennies are in the wallet. Take out 2 without replacement. Penny first, so it's going to be 9 out of 16. Without replacement, so the second pick is going to be out of 15. And now we want a dime, so 7 out of 15. 3, that's 5, going to be 7 over 21 over 8. The second part, penny first and then penny. So 9 out of 16, that's penny. Someone picked out the penny already, so it's now out of 15. And instead of having 9, we have 8 to it. That's 1, that's 2, that's 3, that's 5. That's example 5. Actually, not 5 on the bottom, is a 10. Okay, number 6. A basket has 4 plums, 6 peaches, and 5 oranges. First, orange. That's 5 in total. 4 plus 6 plus 5, we have 15 fruit. So it's always going to be 5 out of 15. Then the next one is still an orange, but 1 is already being taken out. So it's going to be 4 out of 14 now. And the third one is a peach. There are 6 peaches, but there are only 13 fruit left. That's how we set it up. Now it's time to do some cross-canceling. That is 1, that is 3, that's 2, that is 7. So it's going to be 4 out of 91. Second part, plum first, that's 4 out of 15. Then peach, which is going to drop a little bit. So 3 over, the total is 14. And the last one, another plum. Since I already picked out 1, so it's now going to be a 3 and is out of 13. Now that is going to be a 2, that is a 7. 3 is gone, that's a 5. So the bottom is going to be 455, and the top is just a 6. That's example 6. Next, we learned earlier that 2 events are independent if they multiply separately, that equals to the intersection. We also learned if they are actually independent. Then we are going to involve the given the conditional probability. So we combine these 2 together. For example, let's look at the first one. Let's look at the first formula. They are the same. Even the PA part is the same. Just this part that is not the same. And that is why if we can prove these 2 things are the same, like PB, same as P, probably a B given A, if we can prove they are the same, that means the event is actually independent. So let's have a look. Number 7. Use the formula to decide if frosting and flavor are independent. Hint, pick any combination. Let's say we're going to pick, just randomly, let's say we're going to pick blue and vanilla. Okay, then we're going to calculate the probability of blue, which is just right here, 12 out of 21, which is 4%. And then we're going to calculate the probability of blue given vanilla. Let's see if that's going to change. So blue given vanilla is going to be blue and vanilla, which is right here, 5. Out of just the vanilla, which is 8. And that means they're not the same, so not independent. Next, now we have a Venn diagram. Use the formula to decide if iPod and cell phone are independent. So this time, let's see, we can calculate the iPod just by the iPod without any precondition. So we have 14 iPods out of a total of 35. Simplifies to be 2/5. The next one, and since we want to check if they're independent, we are going to give it a condition. So let's say it's still iPod. The condition is you actually have cell phone. So let's have a look. Cell phone is going to be right here, the 25, and out of these 25, only the overlapping part, that's the 10, that belongs to iPod. So that simplifies to be 2/5, which they're actually the same. So independent. That's example 8. Now I do want to talk about question 32 in the homework, so let's have a look. This question is asking you to ask, are you less likely to catch a cold if you are taking vitamin C? It didn't tell you what kind of probability you should be checking, but of course, it's going to be a conditional probability. We want to make sure the vitamin C actually works or help with a cold. The two different situations you can check it. One is you didn't take it and get a cold, or you took it and get a cold. So let's have a look. Cold given vitamin C. So if you caught a cold, well, given condition is you took vitamin C, which is right here. These all represents the vitamin C. So 122 plus 17. And out of these, which is 139, out of these 139 who have taken vitamin C, 17 of them actually got a cold. So 17 out of 139. Now I'm going to do it the other way. So you got cold, but also you didn't take vitamin C. You didn't take vitamin C. I should have not vitamin C. That means anywhere outside this circle, so all of these two numbers, which is 31 plus 109. As for the top, you're looking for code in this area in the two blue circle numbers. 31 is close to the code, so that is actually the code, which is 31 over 140. If you compare to these two numbers, you can clearly see 17 out of 139 is less than the 31 out of 140, which means, yes, it is less likely to catch a cold if you are taking vitamin C. That is everything for 10.5 and 10.6. Thank you.